Hello everyone, this is my presentation for the final project. There are three parts: the review of AXIS stated IBNR estimates, the evaluation of expected loss ratio assumptions, and the independent estimates of IBNR using four reserving methods. First part is the evaluation of the IBNR and ultimate losses estimates computed by AXIS. So to evaluate AXIS, IBNR, and ultimate loss estimates, I first extracted the paid and reported losses triangles from the original Excel file. So I focused on accident years 2008 to 2011 as they were the most mature and they had sufficient development history. So for each development step, such as 12 to 24 months, I calculate the link ratios using the formula here. The link ratio equals to loss at later month over loss at earlier month. I then average these ratios across the selected years to estimate development patterns. So to calculate the CDF from 12 to 16 months, I multiply this ratio at averages. And since later development steps were missing for newer years, I used the accident year 2008 to calculate the tail factor from 60 to 120 months. So the tail factor equals to loss at 120 months over loss at 60 months. So combining the above, we will get the final CDF is the CDF 12 to 60 multiplied by the tail factor, and the result is 5.0063 for the pay loss. So it is the same. So we use the same method for both pay loss and reported loss, and so we get a final CDF of 2.10 for the reported CDF. I then apply the CDFs to observe 12-month losses for 2008, 2013, 14, and 15. So using the formula, we get the ultimate losses equals to the observed losses time multiplies the CDF, and the IBNR here we will get it by the ultimate losses minus the observed losses. So to reflect the possibility of late emerging claims beyond 120 months, I applied a tail factor of 1.01, extending the projections to theoretical completion. So then my ultimate infinity equals to my ultimate losses multiplied by 1.01, and my IBNR to infinity equals to the ultimate to infinity minus the observed losses. So when comparing my results with AXIS original IBNR estimate, I found that my projections were consistently higher across all years. For example, in 2008, AXIS estimates IBNR at just $66,000, while my method estimates over $1.3 million. In 2014, AXIS estimates about $560,000, while I estimate over $1.57 million. This discrepancy is primarily due to my use of long-term development factors based on more mature data, and the application of a conservative tail factor for claims development beyond 120 months. This adjustment results in more conservative and forward-looking estimates, especially for long-tail exposures. Then we can go to the second part. I evaluate the reasonableness of AXIS expected loss ratio assumptions. So AXIS use 65% ALR for accident years 2008 to 2015 and 75% for 2016 and 2017. To test these assumptions, I calculated the actual loss ratios by dividing ultimate losses by earned premiums for each year. So most years align reasonably well with the assumed ALR. For example, 2014 and 2015 were close to 65%. However, there were some notable outliers. In 2000 and 2011, the actual loss ratio was 84%, suggesting the ALR may have been too low. In contrast, in 2013, the actual loss ratio is around 59%, indicating the assumption may have been conservative. So for 2016 and 2017, the actual ratios were 69% and 84%, which are also close with the 75% assumption. Overall, the ALR assumptions appear reasonable, but continued monitoring is recommended to ensure they stay aligned with the actual experience. Then we come to the third part, comparing 4 loss reserving methods applied to accident years 2013 to 2015. The first is the chain ladder method. This is the same as what I do in part 1. I calculated age-to-age factors using historical paid data and selected CDF of 5.0564 after tailing of 1.01 for ultimate development. Applying this to the latest paid losses gave IBNRs of approximately $6.35 million, $6.4 million, and $5.24 million for 2013 to 2015. IBNR is calculated as estimated loss minus paid-off loss to date. This method depends entirely on the shape of the triangle and assumes past development will continue. Then we have the second method, the expected loss ratio methods. Using a 65% ALR, I multiply it by earned premiums to get projected ultimate losses and then subtracted the pay-to-date losses. The resulting IBNR ranged from $843,000 to $1.1 million. This method is simple and useful when triangle data is limited. And then we have the Bornhuetter-Ferguson method. Here I use the same ALR but only applied it to the undeveloped portion with CDF equals to 5.0063. I assume 20% of losses were paid and 80% remained. I calculate the expected remaining losses using the formula expected remaining equals to ALR times premium times the remaining, and adding this to pay to date give ultimate losses of $3.2 million to $3.6 million with IBNR around 1.92 to $2.01 million. So the BF method provides a middle ground by stabilizing projections with expected loss ratios. And then finally we have the Cape Cod method. Instead of a fixed ALR, I estimate one from actual paid losses and development to date. With around 20% developed, the model implied an ALR of 197%, and ultimate losses exceed $7 million for each year. This produced very large IBNR values, of $5.7 million to $6 million. While useful, this method can overreact when early data is sparse. So to conclude, each method offers a different perspective. Chain ladder and Cape Cod are data-driven but volatile. ALR and BF methods offer more stable projections in early development years. A combined view helps ensure that our reserves are both adequate and reasonable. And that's the end of my presentation. Thank you.